Hello everyone. All right, so what you're going to try to do is in this problem is we are going to basically evaluate these sums. Sorry about my handwriting. Evaluate the sum using the perturbation method. So before doing that, let us look into go briefly about what perturbation is actually. And in the most simplistic manner, the perturbation method is basically trying to split a sequence and carrying it out manipulating it algebraically so that we will find some kind of relation for the desired sum. So let's say we have a sum which is Sn equals to sum from k to k equals to 1 to n for a sub k. So basically what we do is in a like in evaluation of the sum using perturbation method is basically we try to find out like expressions for Sn plus 1 summation. So in doing that we try to do a kind of like splitting like procedure, and by that I basically mean that Sn plus 1 for this sequence can be written as a1 plus summation of the summation of the sequence, summation of the expression from k equals to 2 to n plus 1 a sub k. And this is we call is like splitting of the first term, right? And we can also like do a splitting the last term. Like basically what we can do is we can write Sn plus 1 as summation k equals to 1 to n a sub k plus a n plus 1. So basically what we will do is we will write this kind of expression for the given sum that we need to evaluate, and then we will do some kind of an algebraic manipulation, think about it, like do some brainstorming, and we will eventually land on to finding Sn. So even though this process this idea of perturbation is it doesn't descriptively doesn't say steps, but after we start to do this kind of splitting of first term and splitting of last term, we'll basically have an idea of what we will basically have an idea of how we can get Sn. So all right, so let's get started with our equation. So let's start with Sn. So we basically have Sn equals to summation of k equals to 0 and minus 1 to the power n minus k. All right. So our job is to evaluate this sum. So what we can do about is we will apply perturbation method and we start splitting it for Sn plus 1 summation. So let's start with splitting the first term. All right, so if we were to split the first term for the sequence, that will be equal to minus 1 to the power n plus 1 minus 0, and then plus summation from k equals to 1 to n plus 1 minus 1 n plus 1 minus k. All right, so this thing is just basically going to be minus 1 to the power n plus 1. And furthermore, so what we can do with this kind of summation is there's some kind of rule that will allow us to write this thing as k plus 1 equals to 1 n plus 1, provided that we change the k to k plus 1 over here. All right, so that as a matter of fact gives a certain certain conceptual liberty that we can write this entire sequence as starting from k equals to 0. Let me write this more clearly. All right, so k equals to 0 to n and minus 1. So provided that this was n plus 1, over here we can write this as n minus k. All right, so here is some kind of a realization. This term basically over here is just Sn, right? over here. So we can just write down S sub n over here. So here you go. We got our evaluation of splitting of first term for the given summation. So S n plus 1 can be written as minus 1 n plus 1 plus S sub n. All right, let's hold on to that. All right, now we will start to do splitting of last term. So let's do that, and let's realize what we can, like, get from that. So basically we have Sn plus 1, and if we were to split off our last term, so we will get k is equals to 0 sub to n minus 1 to the power n plus 1 minus k, plus, and our last term is going to be minus 1 to the power n plus 1 minus n plus 1. All right, and this thing is going to stay the same. We are not going to do anything with this for now, at least. And realize this is n plus 1 minus n plus 1. That will cancel out, boom boom, and then we will get minus 1 to the power 0, which is basically 1. So this thing is going to be just 1. And here over here, this is going to be negative of summation of k to 0 and minus 1 to the power n minus k. Why is that? Basically, what we can think of is this as, like, let's say we have minus 1 to the power a plus 1. This is simply saying that minus a times minus 1 to the power 1, and this thing is negative 1, so which is just basically going to be negative minus 1 to the power a, right? We're trying to, like, like apply that same concept onto this thing and evaluating it, and then this thing over here is basically Sn. So this thing will come out to be negative some S sub n plus 1. All right, so we got another expression for Sn plus 1 by splitting up the last term, and that was negative Sn plus 1. That sounds good. So now using these two equations, like these two expressions, I'm going to compare them both, and that will eventually give me minus 1 to the power n plus 1 plus Sn equals to minus Sn plus 1. So this thing, like some basic algebra, and we will get 2Sn equals to 1 minus 1 to the power n plus 1. All right, here goes the same rule that we used over here. This will make this out to be 1 plus minus 1 to the power n, 2Sn. And then which will say that Sn is 1/2 of 1 plus minus 1 to the power n. That doesn't look bad, right? That's all right. So we find somewhat of a closed form for our summation, and then we're gonna hold on to that, because I took the liberty of doing this question before starting this video, and I just realized that when I started perturbating for the, like, for Sn, for Tn, and for Un, I just realized that, like, it will, like, all this summation will go hand in hand, and we will be using this in later steps, like, this closed form. So all right, basically I'm gonna go ahead and start off with evaluating for Tn now. So we have Tn is equals to summation k equals to 0 and minus 1 to the power n minus k times k. All right, so this is just times k to this whole minus 1 to the power n minus k expression. So we will again apply perturbation, and we will start by splitting up the first term. And if we were to split up the first term for the Tn plus 1 summation, we will be getting minus 1 to the power n plus 1 minus 0 times 0. All right, plus summation k equals to 1 to n plus 1 minus 1 to the power n plus 1 minus k times k. All right, so this is multiplied by 0 over here. So, so this whole expression is going to be 0. So don't worry about it, right? And then we can write this thing over here as k plus 1 equals to 1, n plus 1 minus 1 to the power n plus 1 minus k plus 1 times k plus 1. All right, remember that, you know, the thing we discussed about here, like provided I'm gonna, if I'm were to like write this expression over here, I'm gonna have to change all my k's that is in this expression to k plus 1. So basically I did the same thing, like to get a clear idea of what I'm gonna do next. So this thing is gonna be like, this thing is gonna be k equals to 0 to n minus 1 and minus k times k plus 1. Hmm, that ain't bad. So that will actually help us to like split this thing by multiplying it. You know, this is k plus 1, and then I can multiply the sequence and actually distribute it. And after distributing it, I will actually get rather uh, what can I call it? A rather pleasing answer. Look at this: minus 1 and minus k times k plus sigma, and then k equals to 0 to n and minus 1 and minus k. Now look at this. This thing over here is basically what we were evaluating, which we used to call Sn, right? That's a good thing. And this over here is basically Tn. So we will write this down as Tn plus Sn. So we got our first part for Tn plus 1. Let me write that down. Thread 2n plus 1 is Tn plus Sn. And this is what we got after splitting the first term. Now our like process is not yet complete. Now we are going to start by splitting the Tn plus 1 from the last term. And if we were to split it from the last term, we will get something like this. So 2n plus 1, k equals to 0 to n minus 1 to the power n plus 1 minus k times k plus minus 1 to the power n plus 1 minus n plus 1 times n plus 1. Now this thing is going to be minus summation k equals to 0 to n minus 1 and minus k. All right, so this minus is explained before, you know, due to the fact that we have a plus 1 over here to the power of minus 1. And then we will go ahead and see that this thing is cancels out, and this is going to be 1, and then that will leave us with this n plus 1 over here. Now look at this. This thing is basically this thing over here. Oh, I forgot the key. Oh, I'm so sorry. All right, now this thing over here is basically gonna be Tn. All right, so that will give us negative of Tn plus n minus 1. Sorry, n plus 1. I'm so sorry about my tongue slip, but that is n plus 1. All right, so what we got for Tn plus 1 after splitting it from the last term is minus Tn plus n plus 1. All right, so I'm going to compare this and this together. And I will just basically try to evaluate an expression for Tn. And then that will be simply Tn plus Sn is equals to negative Tn plus n plus 1. All right. Now, more algebraic simplification. This is 2Tn is equals to n plus 1 minus S of n. All right. So we already know what S sub n is, right? So after plugging it, what our S plus n, which was, go, it was 1/2 of 1 plus minus 1 over n, right? So n plus 1 minus 1/2 of 1 plus minus 1 to the power n, right? Now after doing some simplification, we will realize that this expression is gonna, there will be some algebraic simplification over here. So this is 1 minus 1/2 is gonna give us 1/2 n, and then I have plus 1 minus 1 to the power n, right? which gives us 2t sub n, and this thing is basically gonna be 1/2 of n minus 1 to the power n, right? That is not hard. That is basically easy, right? So we use this thing over here. That is the thing I told at the very first, that we will be using this sum that we will be evaluating, like before, to calculate the sum to evaluate the sum that we will use, like evaluating after. So we will use this thing to calculate over here. So, or I'm so sorry about this. This is not n. This is 1, and then that actually gives us the liberty of writing this thing as, all right, so I'm going to redo this step because I messed up a little bit, but that's what math is, right? Figuring out from your mistakes. So this thing is actually n, 1 minus 1/2 is going to be this 1/2, and then that's just going to basically give me negative minus 1 to the power n, and this is just going to come out to be minus 1/2 n minus 1 to the power n. All right, so this is our Tn. Now let's move on to calculating our third sum, that is un is equals to sigma from k equals to 0, summation from k equals to 0 to n minus 1 to the power n minus k times k squared. So we will going to do the same thing that we did before. We will we'll try to evaluate un plus n by splitting off the first term, and then that will actually give us un plus 1 is equals to minus 1 power n plus 1 minus 0, n plus 1 minus 0, and then times 0, of course, because k is equals to 0, 0 squared 0. So, and then we will evaluate the rest of the summation over here. N plus 1 minus 1 n plus 1 k squared. All right, that doesn't look bad. Now this whole thing is going to turn out to be 0, so all I have to worry about is this, and that also I can write this as k plus 1 equals to 1 n plus 1 minus 1, and that is going to be forgot this minus k over here, sorry about that, and then that will basically going to be n plus 1 minus k plus 1, and the k over here is going to turn out to be k plus 1 squared. All right, now what we're going to do is basically expand this, and then we will try to see what we can do about it. And this thing is going to be k equals to 0 to n. All right, and then minus 1, and of course this thing over here is gonna cancel, this 1 gonna cancel out, and all we are left with n minus k, and then we can expand this k plus 1 to k squared plus 2k plus 1. That's something basic we can do. And then now we're gonna, like, we use our distributive property, and then try to distribute a property to distribute this entire summation by multiplying with this expression, and then that will actually give us, I'm gonna write a little bit below so that it won't like mix up. So that will give us k equals to 0 to n minus 1 n minus k square. All right, that looks familiar, right? So 2 times summation of k equals to 0 to n minus 1 n minus k times k plus summation from k equals to 0 to n minus 1 n minus k by itself. Now that's what I'm telling, like, all our solutions going to help us build the further solutions. So this is basically what, nothing but Sn. This thing over here, that is Tn, and this thing over here is Un. So we can write this whole thing as U sub n plus 2t sub n plus sub n. So we have our general expression, we have our expression actually for un plus 1 by splitting the first term. So un plus 2tn plus sn, and I'm going to hold on to this. Now we have a second step to do, and that will be basically like trying to split up the last splitting up from the last term, and then I'm going to write that down as un plus 1 is equals to summation of k equals to 0 to n minus 1 to the power n plus 1 minus k times k square plus, and our last term is minus 1 to the power n plus 1 minus n plus 1 n plus 1 square. All right, and this thing is gonna be minus k equals to 0 to n because of this 1 over here, as I told before. And then, sorry about that thing, square, and that is gonna be n minus k times k square, and this thing is only gonna be n plus 1 square. Now this thing is just basically minus un u sub n plus n plus 1 square. Now we got our like evaluation of un plus 1 by splitting of the last term as minus un plus n plus 1 square. All right, so now I'm gonna compare this to compare this two and try to find out an expression for un. So that will give me that un plus 2 t sub n plus s sub n equals to n plus 1 square minus u sub n. Now, which is going to give me 2 u sub n is n plus 1 square minus 2 t sub n minus s sub n. And after plugging in all the values and trying my best to simplify, it will give me 1/2 n plus 1 square. Sorry, not that. Let me write this down. So I'm gonna at least write down what those are. So this is gonna be n plus 1 whole square minus 2, and the tn that we calculated was basically 1/2 of n minus 1 to the power n. All right, and then our Sn was nothing but 1/2 of 1 plus minus 1 to the power n, and then we will do our simplification, and then that will basically land us to 1/2 of n squared plus n, and this is going to be our closed form for un. So provided I don't have much time, I didn't do much simplification, but I guarantee you after countless algebraic simplification we will land on to this. So let me write this down. So Sn was basically what? 1/2 1/2, sorry, this is one. I always confuse this with something else. So 1. So our Sn is 1 plus minus 1. Ooh, what is happening? So all right, so 1 plus minus 1 to the power n, and then our tn is basically 1/2 of n minus 1 to the power n, and our un is 1/2 of n squared plus n. All right, this is what we get after evaluating our summation using perturbation method. Alrighty, and that would be all.